Let's talk a little bit about the viscosity and Stokes things, right? Take a look at a problem like this, right? We've got this piece, a very small piece of basalt. This is like silt, right? Okay, and it's settling through a fluid. So let's draw a picture of this. Here's this thing, and it's of course a sphere, right? And as this thing moves through the fluid, remember that you've got what the force of gravity is down, mg, right? And then you've got two upward forces. One is the this force here, right? The one that we're just learned about, right? The force of the drag or the viscosity as it goes through the fluid. But don't forget that you've also got a force, buoyant force, right? And I'm trying to draw this arrow about a third the length of the weight. Okay, and the reason for that is if you look at the buoyancy here, right? The gravity is going to depend on the density of the basalt. The buoyant force is going to depend on the density of the water, right? And so remember that there is sort of a kind of an unofficial thing, right? That the net force either downward or upward, downward in the case of something that sinks, or upward in the case of something that floats, right? And that is that it's basically the net force, okay, is going to be, and we can just kind of look at this as our guide, right? Density minus density, right, times the volume times g, right? So this looks like if it's a bunch of spheres, right? In this case, we would say density of the basalt minus the density of the water, and then the volume is just the volume of this little sphere times g, right? And then that's going to equal this drag force here, this 6 pi viscosity rv, right? Okay, so you can kind of cut to the chase on these things and just be like, I mean, you can make these really complicated, right? You can say this plus this equals this. But, this is kind of where it ends up. And then even, people have solved this for what V is in terms of R. Notice that there's an R on both sides, so it ends up being proportional to the cross-sectional area of R. Okay, let's just take a look. I've got some videos here that I wanted to show you guys. So this is something settling, right? Let's play this.
In fact, in this situation, we can see that there's in fact a graded bedding at the bottom that formed in just a few seconds.
Graded bedding, that means
quite a bit of material stayed in the water
particles
column
at the bottom, right?
To a time lapse.
So they wait. And notice that after about 80 minutes or so,
here,
okay, that this thing is settled.
Coarse material at the bottom, finer material at the top.
So notice that at the bottom here you've got really coarse stuff, and it gets finer and finer and finer until finally you get like the mud, right? And you can see particles still settling here. That's what we're solving for, right? If you've never known how to solve that way, there it is, right? Here's some person also mixing up, right?
Since this process by which
And
heavier
this
and
is after a
insoluble
while,
settle
right?
down.
So you can see after a while it settles out. And if you look at that, you can see a boundary. Here's the coarse particles. They come out of this fast. The lighter particles come out more slowly, right? Because that velocity depends on the size. The smaller the particle, the slower it settles, which we kind of know, right? Watch this one. This is, I think, Western Washington or something.
Allowed to settle.
I really like the music for this. I feel like this is like... Pretty soon here they're going to zoom in on it. 15 people didn't like it. I feel like we should like it. I like this. Anyway, check it out. So you can see on the bottom, coarse, and then the medium, and then the fine. In fact, they actually sorted this before they put it in.
Larger particles settled quicker, so are at the bottom.
Yep. Okay, so if you look at this relationship here, the velocity ends up being, we can cross off this r, right? The velocity ends up being proportional to r squared, right? So if you double the radius, you're actually going to quadruple the speed with which it settles through the water. Anyway, just thought I'd give you that clue, and I think I give it to you in some of the videos as I'm solving them, because it gets kind of tedious solving these things. Okay, now when can you ignore the buoyant force of the fluid? Well, if it's falling through air, ignore the buoyant force. Okay, unless it's something that's about the density of air. Air has a density of about 1.3 kilograms per cubic meter at sea level. Okay, so we could neglect that. But if you want to be really careful and put the buoyant force of air into this, like a piece of basalt settling through air, you'd still do this. I mean, it's 1 part in 3,000. It's a small correction. Okay, buoyant force of air can't be neglected entirely for careful work, but maybe we're not that careful. I don't know. Anyway, that's what I normally say before classes. Good luck with these.